All right, in our next video, we're going to talk about segments. So first, to define exactly what is a segment. And so a segment is a part of a line with two end points. And it has length that you can measure. So a segment is, it's like a line, but it doesn't go on infinitely in opposite directions. It goes on finitely in both directions. So a segment, as I said, is something you can measure. It's finite. It is not infinite. And the endpoints are basically your beginning and ending points. Does it matter which one's the beginning and which one's the ending? And no, it won't matter which one's the beginning and which one's the ending. So just like with lines, lines could be viewed from left to right or right to left. Segments are also going to be viewed in that same way. So what's a segment look like? Well, it's got at least 2 points on it. Typically, it only has 2 points, but it could have more than 2 points. And you'll notice that it doesn't have the arrow caps that go past the 2 points there. Okay, so it has 2 end points. So on the ends are truly points. And then how do we write it mathematically? Well, this is going to be like a line. And so we can read it again forwards or backwards, left to right, right to left, up, down, down, up. And you're going to use those 2 end points to name it, but again in either direction. And we're just going to put a little flat segment on top of there. So notice there are no little arrow caps on either end. And sometimes I've seen students do this, and this would be something I would not do. So I'm showing you something, don't do this. I've seen students put little points on the ends up there so that it really looks like a little miniature, a little baby segment. But then sometimes people will get in a rush when they do that, and they'll put 2 points up here, and then to me it may look like they're trying to say it's a line. So don't put anything on the top of that little baby segment. Just make it a flat line, right? Just go your 2 points and then flat horizontal line right above it. All right, first example, name all of the unique segments on line M. So if you remember from our previous video, in our first video, line M was a unique way to name a line if you had a lowercase cursive letter on one of the ends. And so you'll notice we've got 4 points on this line, right? 4 defined points, points A, point B, point C, and point D. So again, we only need 2 points to name a segment, and it depends on which segment we want to talk about. So initially, I know a lot of students will go, well, look, here's a segment right here. Here's segment AB, okay? And they go, well, here's a segment right here. Here's segment BC or CB. It doesn't matter. Most of these I'll do from left to right. And here's segment CD, and there's only 3 unique segments on here. And I would say, well, there are some bigger segments on here. So just like with lines, you need 2 points, but it depends on which segment you really want to focus on. So you are allowed to skip over points if you wanted to talk about, let's say, a longer segment. So what if I wanted to talk about a segment whose end points were point A and point C, and I want to talk about this entire segment right here? Well, there would be segment AC. And so likewise, what if I started at B and went to D, and I talked about this whole segment from B to D? And so that would be segment BD. And so we could stretch out even further and go, what if I wanted to talk about this entire big segment from A all the way to D? Well, we could have segment AD. And so now at that point, other than just, switching the 2 letters, these are the 6 unique segments that exist here. There are no other segments that we could really talk about that would be unique in this scenario. Now, if 2 segments, and notice, look here, I have 2 segments here that have equal measure. I'm saying that this segment ZX and this segment CV both are 25 centimeters long, so they are equal in measure to each other, then we can call those segments congruent. So this will be more of a newer geometrical term here, but congruent is really just a fancy way of saying things are equal. We say things are equal whenever we can apply a number to them, like 25 centimeters, but if I just wanted to say flat out that segment ZX and segment CV were of equal measure without actually mentioning the 25 centimeter part, then I would use the word congruent instead. So we would write segment ZX is congruent to segment CV. And geometrically, or mathematically, the symbol for is congruent to looks like an equal sign, but it has a little wavy tilde on top of it. So this is how I just do it. Just do an equal sign and then make a little wave on top. So it's kind of nice, we know what equal looks like, right? So equal and congruent look very similar to each other. Congruent is used again whenever we're not talking about specific numerical values. Equal is when you do want to talk about a specific numerical value. So again, notice down here, this is where if I just want to say that they are the same, but I'm not given a specific number, then I would use the congruent symbol. All right, now in this scenario here, and you'll notice in some slides here, I'll have an X somewhere on the screen, and that just means you're not going to have to write any of this part down. This is just something I want you to kind of, put your pen or pencil down and just kind of walk with me on this particular slide. So let's talk about what this picture is saying. Okay, so let's talk about some conclusions. We'll talk about some very easy conclusions that we can reach, and then we'll talk about some extra conclusions that we really have to put some pieces together here. All right, so you'll notice that there's a 3, and it really looks like it's in between the A and the B. So what that is telling us, a conclusion that we can draw, is that segment AB is equal to, remember we're not going to say congruent to because we have a specific number here, but segment AB has a measure that is equal to 3. And we can see the 5 is really between the B and the C, so we're saying that segment BC is equal to 5. Now we don't have any units, and that's fine. We'll just leave these numbers here. Now, some other conclusions that we could reach here is it appears to be that points A, B, and C, they look like they're making a straight line. So we could conclude that points A, B, and C are collinear to each other. Okay, so that's a conclusion that we could reach there. Now, really the only other conclusion that I want you to kind of think about and draw here is, if you have this segment AB and it's right next to this segment BC, and this piece is 3 and this piece is 5, well, what would then be true about the length of segment AC? And some of you might be going like, is it really this easy? Yeah, in some cases it is really this easy. Are we always going to do super easy problems? Not necessarily, but we got to start somewhere, right? So segment AC is made up of this 3-segment piece and this 5-segment piece, and if I add them together, well then I know that the whole segment has to have a length of 8. So that's kind of the next thing we're going to talk about here. All right? So there's this thing called the segment addition postulate. And remember, a postulate from the first video is just an accepted truth. All right, we don't have to prove that this is true. And so for the segment addition postulate, we're literally doing those two things. We're taking segments, and we're going to add them together. And sometimes we can do the opposite of adding. We could talk about subtraction, but it's really that same idea. Okay? So if points A, B, and C are collinear, so again, notice I got 3 points. They appear to be on a straight line, so we can do that there. And B is between A and C. Now, notice I didn't say that it's directly in between A and C. So it doesn't matter where B is. B could be directly in between A and C, but notice I've got B more towards C than I do A. All right? So it doesn't matter. As long as B is somewhere in between A and C, it doesn't matter where it goes. So the segment addition postulate tells us if we take this smaller segment, segment AB, and we add to it the other segment that is connected to AB, segment BC, then when we add those two smaller segments together, then we get this entire larger segment, AC. Okay? So I always think of the segment addition postulate like this. Little segment plus little segment equals bigger segment, right? It's kind of like saying 1 plus 1 equals 2, right? Or 2 plus 3 equals 5. Little thing plus little thing makes a bigger thing. Now, here again is another, what I would call an easy example here. But this is where we can also look at the segment addition postulate and it's kind of inverse, right? Instead of the segment addition postulate, we could look at this as the segment subtraction postulate, if you will. So notice the 10 here. It's right in between the D and the E. So we are really saying here that segment DE has a length of 10. And then notice the 16. Sometimes you'll see extra, maybe like an extra, what appears to be a segment, but it's really showing from here at D all the way to here at F. That is a length of 16. So if you ever see a number on a segment, really whatever that number is in the middle of or appears to be in the middle of, right? Like 16 looks like it's in the middle of roughly from D to F. So that is saying that segment DF has a length of 16. Now, it might be kind of hard to see on your screen here, but I'm asking for what is the length of segment EF? And here's segment EF. So if I've got this little segment of 10, and then I've got this segment, which I don't know how long it is, but I know that together those two segments have to make 16. Well, I'm sure some of you might have looked at this initially and went, boom, instantly segment EF has to be equal to 6, right? And that's great. Some of these may be super, super easy for you, but we're going to talk about some examples where maybe it's not going to be so super easy, right? Now, I do want to throw this out here. Some of you, maybe 6 wasn't super obvious, or maybe some of you like order. You want to show some work, which is fantastic. So here's what you could do. I'm asking for what the length of EF is, and let's just say right now you don't look and see those two numbers, all right? So you could say, we don't know what the length of EF is, so let's call it X. Okay, that's the unknown in this problem. But I know by the segment addition postulate that if I take the one little segment DE and I add to it the other segment that I don't know its length EF, that together, when I add them together, it's going to make the bigger segment DF, which has a length of 16. And so now you've made an algebraic equation. And so now we could do a little bit of algebra here. We could subtract 10 from both sides, so that cancels over there. And then we've got x equals the 6. Okay? So there's a way that you could actually, write out some work there for me. Now, here's an example of where it's probably not going to be obvious. Okay? So if AC, segment AC equals 24, and notice segment AC, that is this great big segment. Then determine the lengths of segment AB and segment BC. But now notice that AB and BC don't just have numbers. They have algebraic expressions. Okay? So we're still going to use the segment addition postulate here. So again, let me put the 24 back into play. So we can take the one little segment. So let's take our one little segment, AB. It's got a length of 2x minus 1. And if I add to that little segment the other little segment, BC, if I add to that the 8x minus 5, well, we know altogether that that should make the great big segment AC, 24. And so now I just got to use a little bit of algebra here. Over here on the left side, I've got some like terms that I can combine. So 2x plus 8x. I really got 10 x's altogether over here. I got a minus 1 and a minus 5, which gives me a minus 6 altogether. So then I've simplified this to be 10x minus 6 equals 24. I can add the 6 over to the 24. So now I've got, let me grab a different color here, 10x equals 24 plus 6 is 30. And then last step, I can divide the 10 over, and I can get that x must be 3. Now, is that the final answer? In an algebra class, you would go, hey, yeah, I figured out what x is. But sometimes in geometry, you might be asked to find certain specific things. And I asked for, what's the length of AB and BC? And notice AB is 2x minus 1. But what is x? X is 3. So now we got to take our answer for x and plug it in to get our final answers. All right? So if I plugged 3 into x here, I have 2 times 3, 6 minus 1. So AB, segment AB is equal to 5. And then if I plug 3 into BC's x, 8 times 3 is 24. 24 minus 5 would give us a length of 19. Now, we could just double check to make sure these answers look legit, right? So if I had 5 and 19, if I add those together, do I in fact get 24 for the whole thing? And I do. So I should feel much more confident that my answer of x equals 3 was the actual correct x value that led me to 5 and 19. All right. What if I wanted to put a point exactly in the middle between 2 points? How would we accomplish that? So again, notice up here the x, you don't have to write any of this down. This is just kind of me asking a question here. So again, if I wanted to put a point in between 2 points, how would I do that? And some of you might be thinking like, well, you could get a ruler out and you could see where exactly the middle is between those 2 points. And that would be one valid way of doing that. But we can kind of cheat, if you will, into doing that. So again, if I wanted to put point B exactly between points E and K, again, you could grab a ruler. I think I can get a ruler here. You go, hey, let's see how long it is from here to here. It's like 143, 144. I guess those are millimeters. I could switch this around and we could do this in inches. And so we could divide that in half and we could see ultimately what that would be, right? But we're not going to do that. Oh, now I think I'm stuck with a ruler because I don't see my trash can, so I'm going to throw this down here. There we go. So what we can do is, you might go, does right here about look like the middle? And some of you are like, yeah, I think that looks pretty good. Would you say right here's the middle? And I would start to be like, I think that's way closer to E than it is to K. So at some point, you're just going to have to find, a general middleness. So let's say somewhere in here. Okay? Does that look like it's exactly in the middle? And right now, geometrically, I can't verify that that's exactly in the middle. So we're going to get to use some geometrical markings to make that happen. Okay? So here's what I was meaning earlier. We can kind of cheat, if you will. So we're going to use things called congruent markings. And congruent markings say things have equal value, even if they don't necessarily, quote unquote, look like it. So congruent markings for segments really kind of look like a segment, but they usually go in the exact opposite direction that those segments are in. So what I mean by that is, notice segment EB and BK, they're horizontal segments, right? So a congruent marking in this case would be perpendicular to it. They would be more vertical markings. So what I can do is I could put a little marking about right here, normally where I would see a number if I had a numerical value. So go about right in the middle between E and B and just put a little vertical mark right there. And then we would go put this same mark on our other segment that we want to say is equal. Okay? So if B was in the middle, then from B to E would be the same length as it was from B to K. All right? So here's just kind of an updated picture here. So again, we call those congruent markings, and we see those type of markings specifically on segments. And so what we could say is segment EB is congruent to segment BK. We're saying that they have equal measure without actually saying equal measure. Okay, we don't know how long these two segments really are. They could be 20 feet long each. They could be 2 inches long each. We don't know. But what we're saying is that they are equal. So without those markings, you cannot assume that segment EB is congruent or equal to segment BK. So again, let me just jump back real quick here to this picture. Can I say for certain that segment EB is congruent to segment BK right now in this picture? And I would have to say that is unknown. I mean, it may certainly look like B is in the middle between E and K, and that this segment and this segment would be equal to each other, but there is no indication that that is necessarily true, the way that this is expressed. Now, if I see those markings on there, those markings are telling me geometrically that is true information. Okay, so you have to see those markings, or you may see a vocabulary word used. Now, we may say that a point, we may even have like a line, right? We may have a line that goes through point B here. And we could say that point B, or this line that contains point B, is bisecting the line. Now, bisect, if we kind of split it up here, bi means to, sect means cut. So what we're really saying is point B, or a line that contains point B, is cutting into 2 equal pieces. And so there's segment EB and segment BK. So we can either use the vocabulary word bisect, or we could use the word, this is something we'll talk about much more so in the next video, is midpoint. Point B is the midpoint. It is in the middle between points E and K. All right, so midpoint or bisect kind of represent the same idea there. All right, so example 4. Calculate the length of segment RT. So first let's notice RT, that's this great big segment here, right? And so the other thing that I notice here, there are some special markings. There's those congruent markings. And so what's that telling us? That's telling us that this segment RM has the same measure, has the same length as this segment over here, MT. And so if these two segments are equal to each other, then what should we do with the values that represent their lengths? And what we should do is, if two things are equal, well, we should set them equal, right? And so we can take the 5x plus 9 piece, and we can take the 8x minus 36 piece, and geometrically we know they have to be equal. How do we know that they're equal? Because these markings are telling us that they have to be equal. And so now from this point we've got an algebra equation. You might be going, whoa, I thought I was taking geometry. This is a lot of algebra. You're going to see a lot of algebra in geometry. It's really going to be integrated throughout the entire year. So now if we use some algebra here, let's move my 5x over to the 8x side. That's a 5, not a 3. So then we got 9 equals 3x minus 36. We can then add the 36 over, across the equation to the 9. And then we've got, 45 equals 3x. Divide that 3 over to the 45, and we get that x is equal to 15. Now, keep in mind, x equals 15 is not the final answer here. I want to know what the length of segment RT is. Now, some people might go, but we weren't given an algebra expression for what segment RT is. And that's true. We weren't told like how many x's plus or minus a number represents RT. But what we do have are the individual parts that we know have to be equal. So this is the way that we can kind of double check that. So if we plug 15 into this x, we got 5 times 15, that's 75, plus 9 more makes 84. So I'm just going to put a little 84 up here. So segment RM has a length of 84. And then 8 times 15, oh boy, 8 times 15, that is what? 120? 120 minus 36 gives us a matching 84. Okay? So if this piece is 84 and this piece is 84, then how long is this whole thing from R to T? 84 and 84 together gives us 168. So the length of segment RT is equal to 168. All right? And this is another good way that we can double check to make sure that this really is legit. If I had gotten different numbers, if I didn't get matching 84s here, like let's say I got 84 and 27, well then I messed up my algebra somewhere. This x equals 15 isn't legit unless I just don't know how to plug 15 back into the equations to get matching 84s, right? That could be an issue there. All right, the last problem is for you to try. And again, give this one a whirl. I'm telling you that, from K to C, this is this 2x plus 10. From C to N, segment CN, this is 4x plus 1. And I give you a little bit more information up here. The segment KC has a length of 31. In the end, I want to know how long is segment KN. Okay? So see if you can put together those pieces to set up an equation, to solve, and then ultimately in the end tell me how long is segment KN. And that's all for this video. Good luck. We'll talk about this one the next day in class.